Hello guys, welcome once more to another video on our YouTube channel. So in this video we are going to be looking at a question on rotational dynamics, where we are going to be solving June 2020 further maths paper 3 question 4 Roman 1 only. In the next video I'm going to solve the remaining part of the equation, but in this video I'm just going to show you guys how we can apply the theorems in moments of inertia. Okay, all right, so the question reads, the question says that a plane composite object is made by attaching a thin uniform rod PQ of mass m at right angles to the midpoint AB of a uniform rectangular lamina ABCD of mass small m, given that AB is 6A, BC is 3A, which is equal to PQ as shown in the diagram below. So here is the diagram where we have a rectangular lamina, we have a rod that is attached at right angles to this rectangular lamina, such that the length of the rectangular lamina is 6A, the width is 3A, and the distance from P to Q is also 3A. Now the question is asking us to show that the moment of inertia I of the object, which is this plane composite object, about a smooth horizontal axis L, here is the axis L, through the midpoint of PQ and perpendicular to the plane of the lamina, is given by I to be equal to 314 into 17m plus m, all of that, times a squared. So it is allocated for 3 marks. So without wasting much of your time, let's just get started directly into the video. But before we start, I'm going to like you to watch the videos that I did concerning rotational dynamics. Okay, so I'm going to include the video links of those videos in the description of this video, so that you can get to those videos, and if you're facing difficulties with rotational dynamics, those videos might be of help to you. All right, so let's get started. So I just collected the information that were given to us in the previous slide. All right, we have that the mass of the rod is capital M and the mass of the rectangular lamina ABCD is small m, and this is the diagram that was displayed to us. So we have to show that the moment of inertia of this composite body about the axis L is the axis that is passing through the center of the rod and perpendicular to the plane of the lamina. All right, so for us to show that the moment of inertia of this system is equal to this, we just need to first of all find the moment of inertia of the system. We need to find the moment of inertia of the rod about the axis L. We also find the moment of inertia of the rectangular lamina about the axis L, and we add the two. All right, since the plane composite body is made up of the rod and the rectangular lamina. So we have that the moment of inertia of the system about the axis L is equal to the moment of inertia of the rod about the axis L plus the moment of inertia of the lamina about the axis L. So we are going to find each of these moments of inertia, then we add and simplify to see if we are going to get the proof at last. So how do I get the moment of inertia of the rod about the axis L? Now the moment of inertia of this rod about the axis L is just the moment of inertia of this rod about an axis that is passing through the center of the rod and perpendicular to the plane of the rod. Since they told us that the axis L is perpendicular to the plane of the lamina, and the plane of the lamina is coinciding with the plane of the rod, it therefore means that this axis is also perpendicular to the plane of the rod. And how do I get the moment of inertia of a rod about an axis passing through the center of the rod and perpendicular to the plane of the rod? We can prove that by integration, which I did in one of the videos that I'm going to add in the description of this video, as well as we can just use the standard result. So in this case you are going to use the standard result. All right, so you can always check your formula booklet, but I'm going to give you the standard result. So the moment of inertia of a rod about an axis that is passing through the center and perpendicular to the plane of the rod is the mass of the rod times the square of the length of the rod divided by 12. Okay, so this is the standard result. So I just generated the standard result so that if the length of the rod is given to you, you just need to replace here. Okay, so the mass of the rod was given as capital M. The length of the rod is 3a. We have to square it before dividing by 12. So this just gives you 9ma squared on 12, which simplifies to 3ma squared on 12. We are done with the first quantity. Now we need to find the second quantity, which is the moment of inertia of the lamina about the axis through L. Now you realize that the axis through L is kind of parallel to this axis, that is parallel to the diagonal of the lamina. So since the two axes are parallel, from the parallel axis theorem you realize that there is a distance that is separating the two axes. The two axes are parallel. So if we want to get the moment of inertia of this lamina about the axis L, we are going to apply the parallel axis theorem, which says that the moment of inertia from the parallel axis theorem, the moment of inertia of this lamina about the axis L is equal to the moment of inertia of that lamina about an axis that is passing through the center plus the mass of the lamina times the square of the distance that is separating the two axes. I've just labeled that distance as z. So the moment of inertia, I'm going to repeat again. The parallel axis theorem says that the moment of inertia of this lamina about the axis L, that is about this axis, is equal to the moment of inertia of the same lamina about an axis passing through the center, okay, plus the mass of the lamina times the square of the distance separating this axis passing through the center and the axis L. Okay, I'm taking this diagonal because this diagonal is parallel to this axis passing through the center of the rod. So DB is parallel to L. That's why I'm using the moment of inertia of the lamina about DB, because passing through the center we can also have a vertical and horizontal. Okay, so now we need to find the moment of inertia of this lamina about the diagonal. Okay, and to get it, let me just display to you what we are going to do. So we have a square lamina, we have a rectangular lamina, we have the diagonal. Now to get the moment of inertia of this rectangular lamina about this diagonal, we need to use what we call the perpendicular axis theorem. We are using it because we can find the moment of inertia of this rectangular lamina about the axis vertical, that is the axis perpendicular to it and passing through the center, as well as the axis perpendicular to the width. So this vertical axis is perpendicular to the length and the horizontal axis is perpendicular to the width. So if we are able to get the moment of inertia about the vertical and horizontal, and you realize that all the three axes are perpendicular, we can now use the perpendicular axis theorem. So if I label those axes x, y, and z, then from the perpendicular axis theorem, the moment of inertia about z, which is actually what we need here, is equal to the sum of the moments of inertias about x and about y. Okay, since the three axes are perpendicular to each other, and the moment of inertia of this lamina about z is just the moment of inertia about the diagonal. So the moment of inertia about z, like we said, is the moment of inertia about x plus the moment of inertia about y. Now what is the moment of, let's begin with the moment of inertia about y. The moment of inertia about y is simply the moment of inertia of this rectangular lamina about an axis that is perpendicular to the length. Now think about this rectangular lamina as a rod that has been stretched. You realize that we are just going to take the same formula, the mass of the lamina times the length of the lamina squared divided by 12. Now if we are looking for Ix, okay, Ix is now the moment of inertia of this rectangular lamina about an axis passing through the center, but this axis is now perpendicular to the width. Okay, because the width is vertical, so the axis is perpendicular to the width. Since the axis is horizontal, we now see the mass of the lamina times the square of the width divided by 12. So the axis must always be perpendicular to the figure itself. Okay, so like I said, if we are dealing with the rod, Okay, we need to take the mass of the rod because it's passing through the center. Let me specify the mass of the rod, the square of the length of the rod, okay, divided by 12, because the axis is perpendicular to the length of the rod. But in this case, if we are taking about y, you realize that the axis is perpendicular to the length of the lamina, so it stays the same. That's what we call the stretching rule. But now when we are finding Ix, since the rod is instead perpendicular to the width, we change the length to the width. Okay, so if we simplify, we get the length of the rod is 6a. When we square, we have, this is it, 6a, we have 36. Then the width of the rod is 3a. When we square, we have 9. If we simplify this, it gives us 15 ma squared divided by 4. So what now is going to give us, what is going to be the moment of inertia, what is going to be the moment of inertia of the rectangular lamina about the axis L? Now we have already found this iz here is simply the moment of inertia of the rectangular lamina about the diagonal, which is dB. So I've just replaced this quantity here with 15 ma squared divided by 4. The mass of the lamina is small m. Now what is the distance d? Is the distance separating this diagonal and the axis L. And since this is a center, then this small distance here is simply half of the width, which is 3a divided by 2. Now since this is also the center of the rod, then this distance from P to the center is the length of the rod PQ divided by 2. But fortunately the length of the rod is 3a, so we have 3a divided by 2 for both distances. So the distance d is the distance from the center of the lamina to the line AB plus the distance from P to the center of the rod, which is 3a on 2 plus 3a on 2. 3a on 2 plus 3a on 2 is just 3a. When we square it, we get 9a squared. So it means that this gives us 15 on 4 ma squared plus 3a all squared. And if you simplify, it gives you 51 on 4 ma squared. Now, the moment of inertia of the system about the axis is the sum of the moments of inertia of the individual bodies about the axis, which is 3 ma squared on 4 for the first one and 51 ma squared on 4 for the second one. So we can write 51 as 3 times 17, and if we factor out 3 divided by 4a squared, we are going to have 3 all over 4. From here you're going to be left with capital M, since you have already factorized the a squared, and if you remove 3 over 4 from here, you're going to be left with small m, since you have removed the a squared, and this gives us a proof. So you have proven that the moment of inertia of this system about an axis passing through L, which is passing through the center of the rod and perpendicular to the plane of the lamina, is 3/4 into capital M plus 17 small m times a squared, and we are done with the equation. Alright, so like I said, if you're facing difficulties with this topic, it is preferable that you begin studying the topic from the beginning. And to study the topic from the beginning here in my channel, you just go to the links that I have added in the description of this video. I've put the links in order. We have video 1, video 2, video 3. So try to study in that order so that you try to get a little mastery of the topic, or maybe an overall idea about the topic, provided you have not done the topic yet in school. If you have done the topic yet in school, it means that at least you're perfectly understanding what I'm saying. Anyways, if this video has helped you in one way or the other, try to like the video, share the video with your friends, subscribe to the channel, and stay tuned. See you in the next video.